We talked about probability distributions, and one of the main ones that gets talked about pretty much anywhere you go is what's called a binomial distribution. And once I get done with this, we'll talk about another one that's called Bernoulli. It's very close to this. We probably won't talk about it that much because a binomial is just a Bernoulli one that got added up for you. So that's the more helpful one anyways, because it just adds them up for you. So here it says a binomial experiment. Obviously, you think of the word two, right? Possibilities. It is a probability experiment, just like we've been doing. So we know that it does have to be, every probability has to be between 0 and 1, and they all have to add up to 1 when you're done. But there are some more conditions here. These are the 4 main ones. That experiment has to be repeated for a certain number of trials. Maybe it's 2 trials, maybe it's 1,000 times you did it. But there's a certain number of trials that you're going to keep going. And that's normally called n, as you can see down here. The symbol for n is basically the number of trials repeated. But each trial has to be independent from the other trials. And we kind of repeat that statement here in a second. So basically, you could think of it as that one can't affect the other if you want. But remember, that means with probabilities. It doesn't affect the probability. 2, there are only 2 possible outcomes. Success or failure. Does it say right there that they have to have the same probability? No, just there's a success and a failure. Okay? One could be incredibly possible, and the other one then obviously won't be, because they have to add to 1. Okay? The probability of success, which we'll call P of S, is the same for each trial. So if the probability for the first trial was 1/6, the second trial, the probability of success better be 1/6. Well, isn't that kind of the independent thing that we already said? All right. And obviously, if the probability of success is 1/6, probability of failure has to be 5/6. So if you say the probability of success has to be the same, you're really saying the probability of failure also has to be the same for each trial. But a lot of people, when they see binomial, they think the probability of success is a half. Probability of failing is a half. Is that necessarily true? No, as long as it's the same probability for success each time, you're fine. Could be 1 out of 100. Could be 1 out of 1,000,000. But as long as it's the same every time, you're good. And the random variable x, that's what we call it, it actually just counts the number of successful trials. That's what it does. And we're going to kind of show you, I'm going to show you the longer method of doing this, and then I'll show you how the formula is really nice. And that's what we're kind of going to talk about today. And as you can see, it says day 1. In day 2, there's actually tables people made. You can just follow the table, and it'll just give you the answer. And then, yes, your calculators will do this quite simply. Okay? But we're going to save that for tomorrow until you have a little bit better understanding. So probability of success is going to be P, a lot of times is what they're going to call it in the formula, or P of S, and that's the probability for a single trial. Q, which will be P of F, your failure, is called Q, which is really just 1 minus P, right? That's the complement. Right? And then X is just the random, represents the count of how many times you were successful of n trials, and you notice you could be successful 0 times, or 1, or 2, or 3, all the way to n, right? Because if we had 20 trials, do you agree it could be successful all 20? Right? Especially if the probability is very high. It could be all 20, but it could be anywhere in between there as well, correct? It could never be successful. So any questions on this first page? Because we're going to refer back to it a lot. So decide whether this experiment is binomial or not. If it is, specify the values of n, p, and q, and list the possible values that x can actually hold, and then if not, explain why. So there's a surgery out there that is 85% chance of success. So obviously, it can fail. A doctor performs the procedure on 8 patients, maybe in one day, maybe who knows, it could be 10 different days. The random variable represents the number of successful surgeries. Well, how would you check to see if that's binomial? Well, look at 1 through 4. If you say yes for all of them, if it meets that criteria, then yes, it's binomial. So here we go. What do you think for number 1? Do you believe that it's repeated a fixed number of times? How many times? 8. So is it fixed? Yeah, fixed number. Where each trial is independent of the other. Does the first surgery affect the second surgery, the probability? No. Okay, so has it met criteria 1? Yeah, we're good. So yes, or check mark or whatever you want to do. Criteria 2 says there are only two possible outcomes of interest.
Yes.
They can be classified as success or failure. Well, here success is live, right? We're assuming. And failure is death. So are there a success and a failure? Is there any other outcome? No. Either you live or you die. All right? So yeah. All right. 3. Probability of success is the same for each trial. Again, I think that's almost a repeat of, it's very similar to repeating the first one in a way. And yeah, each one is the same. And what's our last one here? It's the number of successful trials. So is it something I can count? Number of successful trials. It is. And it says right here that that's what X is going to tell us, is that it's the number of successful. So according to that, is this binomial? Yes, it is. So if it is, I should be able to give you N, I should be able to give you P, I should be able to give you Q, and I should be able to tell you what X can be, right? I should be able to give you a list of all the values that X can hold. So N, well, N is the number of trials repeated, or the number of times this is done over and over again. How many times are we doing it? You already told me that. You already told me it was 8. We're having 8 surgeries, right? 8 patients, the surgery went over and over again. P, again, is your probability of success, which, and let's change that over to be 0.85, right? Because we want to make sure that these two add to 1, right? So let's just kind of change that over to 0.85. And so Q is unfortunately your failure, so you can just do 1 minus that. It is the complement, because again, it's only 2 outcomes, right? Only 2 possibilities. And so, again, that 2 possibilities is one of the reasons they call it binomial, okay? So X is going to be a list of some kind, so we'll put it in some kind of list notation. So is it possible for the random variable, that's the count of successes, is it possible that it would be 0 out of 8? Can that happen? Could it be 0? Yep. Could it possibly be 1 success? It could. And it could be 2, correct? Now let's just use the ellipsis to speed things up. Ending us where? 8. Right? Because it is impossible to have 9 successes out of 8 trials. Okay? So there are all your possibilities. This is just listing all the possibilities. This is what the answer could be. It could be 0, it could be 1, it could be 2, 3, 4, 5, 6, 7, 8. Number of successes. But you can't have 9. Is it probable that he'll have all 8? I'm just asking, is it possible is really what I'm asking here. Is it possible all 8? Yes. Is it possible none of them will be successful? Is it probable? No. Possible? Yes. You see the very 2 closely related words there. Possible, probable. Right now, when you're listing all the possibilities of X, it's just, is it possible? And yes, it is. And that has to be finite. That has to be, I have to be able to figure that out because N trials. 0 to N, right? So how about a jar contains 5 red, 9 blue, and 6 green marbles? So we've got a jar. You randomly select 3 marbles from the jar. That could be read 2 different ways, right? That means I pick 3 all at once. Or you could read it that I pick 1, and then I pick another one, and then I pick another one, right? That's 2 ways you could look at that, correct? Without replacement, so I didn't put it back in. So do you agree both of the examples I just gave you was without putting it back in, right? Just grab all 3 at the same time, or grab one, then grab another one, grab another one. Do you agree it could be read either way? And the great thing is it doesn't change our answer which way you did it, okay? The random variable represents the number of red marbles. So we're saying our success is getting a red marble, right? Is that a probability that we could figure out? The probability, like if I just pick 1, is that a probability I could figure out? But they're saying select 3 marbles from a jar. So is the probability of all of those going to be the same? No matter which way I do it. If I pick all 3, or if I pick 1, 2, 3, is the probability of each one of those being red going to be the same? Because I didn't put it back in. So does that probability change? So the probability has been affected, correct? Which means these events are dependent on each other. So if we were to look at our little rules here, 1, 2, wow, that's just perfect. Just put a 3 right there. 2, 3. If we look at our criteria, number 1, yes or no? Is the experiment repeated a fixed number of times? That part, yes. But were each of the trials independent? No. So overall, 1 is a No, and at this point we can just say no overall, but let's just talk about them so that you understand what they mean. Number 2, are there only 2 possible outcomes here? Do I either get a red one or not? Pretty much, right? I get a red one or I don't. So I'd say yes on that one, right? There are 2 possible outcomes. 3, probability of success is the same for each trial. Not necessarily, and again, it depends on how you read that problem. And 4, does that random variable actually count our successes? Would that tell me how many? Well, it would. Yeah, that's what it's saying it is right here, yes. So, but the key is you only need 1 no. 1 no, it's done. Okay, no good. So can I sit here and get N, P, Q? Some of you kind of could, but why would you do that? Because you're not going to use that information anyways. Okay, so this one is a big no for binomial, or N6 apparently. Yes? I was hoping somebody would ask that question. The question was, is if you pick all 3 at once for, would it still be a no for the first one? You could consider that a trial, picking 3. You very well could do that, consider that's the trial. And then would the probability, if I turned around and did that again and picked all 3 again, would really that probability still end up being the same? Much harder to calculate, but it would technically still be the same. Okay. Yeah. Mm-hmm. And that's why I put the without replacement in there, so that you could see that it was 1 at a time. Very good. Excellent. Oh, we are taking a multiple choice quiz. And I'm sure this is how most of you take your multiple choice quizzes. There's 10 questions. Each question has 4 possible answers, only 1 of which is correct. To complete the quiz, you randomly guess the answer to each question. The random variable represents the number of correct answers. Okay, of course, this is how you do it, right? This is how I think some people take the WKC, where they just make a little pattern with their dots. Huh. Well, identify a trial of the, could you agree this is an experiment? Whether it's a binomial experiment, we don't know yet. But this is an experiment of some kind, correct? And what is a success? So there is a success here. So what's a trial of the experiment? What would that be? This is answering a question. Yeah. So answering a question is a trial. And you have how many trials? 10. 10 questions. What's a success? Getting it right. Okay. So at this point, do we still know if it's binomial or not? Yeah, we haven't really looked at our 4 criteria yet, right? So the second question is decide if this satisfies the 4 conditions. So 1. Number 1 on the other side, I'll read it to you, says the experiment is repeated for a fixed number of trials. Mm-hmm. And does each trial have, or is each trial independent from the other trials? Does the first question have anything to do with the second question necessarily? No. So we would say, yeah, this is good, right? 2. There are only 2 possible outcomes of interest. They could be success and fail. Yeah, you either get it right or you get it wrong, right? I don't care if the right answer is A. I don't care if you answer B, C, or D. All of those are wrong, right? Okay. So yeah, we're good. How about number 3? The probability of success is the same for each trial. How do you know? Yeah, there are 4 possible for every single question, correct? And there's only 1 that's right. Okay, so yes. And 4. The random variable counts the number of successful trials. Well, the random variable represents the number of correct answers. Is that the successful trials? Yeah. You already did. You just told me that the correct answers are what's a success. So is this binomial? Yeah, we're good. You're going to get better at identifying binomial as we go through this. You're not going to have to sit there and go, oh, is it? Does it meet number 1? Does it meet number 2? You're going to start knowing. Make a conclusion and identify N, P, and Q and the possible values of X. So your conclusion is that this is most definitely binomial, right? What's N? Remember, what's N stand for again? Number of trials. How many trials are we talking about? 10. All right. What else do we need? P. I think somebody already said this. Is it 1/4? Yeah, 1 out of 4 or 0.25, right? Either way. Well, close enough. Q, probability of failing. Yeah, 3/4 or 0.75. What else do we need? X. So the number together. So what, again, remember, am I saying what's probable here or what's possible? What's possible? Is it possible that I would get none of them correct? Yeah. And I could get just 1, or I could possibly get 2. And again, we'll use the ellipse. Speed things up. 10. It's not possible to get 11 correct out of 10 problems. It's possible to get 10. Okay. I do believe there's a typo on the next little part that you have here, and we'll fix that easy enough. In the box, yeah. Well, it sure would be nice to know how to calculate these things without having to hurt ourselves, right? Yeah, well, good thing they came up with a formula for that. Which, well, I'll fix the typo before you put it down. In a binomial experiment, so you have to know it's binomial, the probability of exactly X successes. So I say in that last one, maybe I want to know what's the probability I get 6 out of the 10 right. You see how many exactly? I want to get 6 out of the 10 right. Or maybe I want to get 2 out of the 10 right. What's the probability? Or maybe I want to get all 10 out of 10 correct. Okay, you see what I mean by exactly then? X out of the n trials is, and the typo is the R, that should be an X. Sorry. So that probability is you take NCX, and I'm going to show you where this comes from. It'll make sense, I believe, when I show you how this works. So again, it's N objects combination X, right? You take the probability of success to the X power, because that's how many successes you want, right? You take the probability of failure to basically, well, how many would you have failed at if you succeeded at X of them? Wouldn't you have failed at the rest of them? That's what N minus X is saying. N's your total number. If you had 10 questions, let's think of it that way. I'm going to take, there's 10 questions. I want to get exactly 3 of them right. Okay? You would take your probability, what was that? You said 1/4 times to the 3rd power. And you would take 3/4 to how many you got wrong, which would be 7 of them. So you see how that works? 3, and that makes sense. And what this is, this formula right here is just your NCR formula. That's all that is. And here's just your P of X just transfers there, and that just transfers there. It looks very, very complicated, but it really isn't. And you'll be happy when I show you how your calculator just spits out this answer. But we'll do it by hand first because we can. And I can make you. Of course, it's a 6-sided number cube. So let's see if you agree that it's binomial, this question. Did I give you enough time to write that down? Or? Yeah, okay. It's rolled 3 times. Determine the probability of rolling exactly 1/6. Is it binomial? Well, what's N? 3. What's P? How do you know it's 1/6? What's a success? Getting a 6, right? Probability of rolling exactly 1/6, right? So the probability of success is 1/6, right? That's what I want to get. So probability of failure is 5/6. And X here that I'm looking for, we realize X is either 0 6s, 1 6, 2 6, or 3 6s, correct? That's the possibility because I rolled it 3 times. Which X am I concerned about here? How many of them do I want? I want 1/6. Yeah, the rest of them have to be something else. Yeah, the other ones have to be something else. Okay, so it is binomial. So you told me N was, again, we're rolling it 3 times. Now you have to figure out what is the success. A success is rolling a 6. And what is that probability? Just given one trial, that probability is 1 out of 6, right? I'm telling you it's a fair-sided die. We'll make that assumption. Q, that you're failing is 6, because there's 6 sides on that thing, right? And only one of them has a 6 on it. Now, if we were doing the old one, x could have equaled, wow, that's horrible, 0, 1, 2, or 3. That's how many successes I could have had, right? But are we concerned about the 0? Is that what I want here? No, do I want 2 of them? Do I want 3 of them? No, I want exactly 1. So I don't care about you, I don't care about you, I don't care about you, I care about you. So that's what x is in this problem. That's the only one I'm concerned about. So, 3, choose, what's x for me? 1. See, I'm filling it in now. Probability of success is 1/6. According to this, I should take it to the x power. 1. I want x to be 1. That's how many I want. 1. And 5/6. Again, when I show you how you used to do this in Algebra 2, it'll make more sense. 5/6. Well, how many of them should be 5/6 then? I'm only rolling this thing 3 times. Take it to the second power, right? Because there's 3 trials total. That's the beauty of these two right here. These two exponents better add to that number out front. Right? Because if you did it 3 times, here's your successes, there's your, they better add up to that. And do you agree that's really what the formula is saying, right? Looks very complicated when you see it at first. Well, let's start doing this. Well, n is what, 3? So 3 factorial over n minus x, that's 2, right? That's right here, n minus x. So 2 factorial, 1 factorial, times 1/6 to the first. Can you, is it okay if I just write 25 over 36 for that? Squaring it, everybody's good with that? Yeah? So yeah, this turns into 25 over 36, right? So again, I'm just basically substituting it in here now. Well, the nice thing is, this is saying 3 factorial, right? So that's saying 3 times 2 times 1, right? Over, this is saying 2 factorial, which is 2 times 1 times another 1, right? So in other words, it's just 3 times 1/6 times 25/36. So I would look at it this way. I can take that 3 times the 6th, makes it 3/6, right? Which is known as 1/2. So it's really 1/2 times 25 over 36, which is 25 over 72. I needed you to know, what x was, what that was, and I just wanted you to know what all that was. Okay, so 25 out of, so about 0.347. All right, what's that mean? Not odds.
Probability.
Yep, probability.
Roll is 6 just one time. 3 rolls with 6 sided number Q is 4.7%.
Do you believe that?
Yeah.
Because it's saying exactly 1/6. It's not saying if I get 2 6s, that's a failure, right? If all 3 of them come up 6s, failure. If none of them come up 6s, failure. So you're going to fail more than you succeed at this attempt, right? Again, you do it 3 times, it's very possible you will fail a lot. Okay? Now, when we were in Algebra 2, did most of you have me for that? I think so. We would say, oh, well, it could go like this. I could get a 1/6, a 5/6, and a 5/6, right? Isn't that how we did it in that class? But then we said that 1/6 could happen any of the 3 spots, right? So we said, okay, so we're going to take this times 3 factorial, and we said, but I wouldn't necessarily be able to tell but the difference between those two, right? I just know they both fail. So that's a repeat. Isn't that the same thing we just did? That's way more complicated. You have to really know what's going on to do it this way. I just did it in black, right? This formula just says here, 1/6 to the first, 5/6 to the second. Boom, there it is. Okay. True, or just remember it's binomial. I'll always give you the formula if you need it. Okay. Once you get to your calculator, you're just going to be able to, you type in what? N, P, and X. Done. Right? You don't have to. It's already in there. I don't think it's in the smaller ones. It's in the 83s, though. And I will show you how to use them, but you need to show me you can do it by hand first. So a card is selected from a deck and replaced. If this experiment is repeated a total of 5 times, calculate the probability of seeing exactly 3 clubs. There's one huge word up there that actually allows us to do this binomial. Replaced. Why wouldn't we be able to use binomial if this didn't have replaced? The probability would change, right? The probability of success would change from one trial to the next, so it wouldn't be independent. And what number 3, I think, says that it's supposed to, right? Probability of success should stay the same. So without replace, yeah, we would not be able to do this. We'd have to kind of do it more this black method, all right, which is much more complicated and takes much more thought, all right? So it is binomial. N is, how do you know that? We repeated it 5 times, okay? P, this could be interesting. Card is selected around, and we want the probability of selecting at least 3 clubs. So the success is picking a club, right? How do you know it's one for it?
13 to a suit.
Yeah, or there's 4 suits, right? And I just want one of them, right? Or there's 13 to a suit and 52 cards, right? So the probability of success is 1/4 because I want to get a club, and it is a quarter of the cards. So then failing is unfortunately much higher again. Is failing always going to be higher? No, not necessarily. I could say picking not a club, and then these two would be switched, right? And which X, now let's talk about all the X's. You don't have to write them all down, but I want you to see this. Do you agree that it's 0, 1, 2, 3, 4, and 5? Do you agree that's how many successes I could get, right? Those are the possibilities. Am I concerned about 0? No. Am I concerned about 1? Now, how many do I want to get? I want to get 3. So the X value I am concerned about is 3. Again, you don't always have to do it that way, but if that helps you, go ahead. Okay. So there's 5 of them. I want to choose exactly 3 of them. Probability of success is 0.25 or 1/4, right? And how many of those do I want? 3. And 0.75. How many of those do I need? I need 2 of them, right? Because remember, here's one way to quickly, these 2 numbers better match. These 2 better add to that. Okay. And of course, can you do 5 choose 3 on your calculator? Yeah, you could do that. Or we can do it by hand because that's fun. 5 factorial over, what, 3 factorial? Well, actually be 2 factorial first, my bad. If you follow the rule. 2 factorial, 3 factorial. You see how these 2 just magically find their way down here? It's amazing. All right. And well, would it be easier fraction or probably, huh? Because we can do that in our head. 1/4 cubed and 3/4 squared, right? So this is basically 5 times 4 times 3 times 2 times 1 over 2 times 1. Yeah, that's a good one. Times 1 times 3 times 2 times 1, right? So slash gone 2. So in other words, 5 choose 3 is 10. All right. So 10 times, again, that's if you had 5 objects and you wanted to choose 3 of them. Order didn't matter, right? That's why this works, because order doesn't matter, right? Okay. And 1/4, that's 1 over what, 64? Times 9 over 16. It reduces to approximately, I don't know, because I have a decimal. Yeah, how come I don't have a fraction on here? That's bizarre. That's very much unlike me. Yeah, oh well. We'll make it work. I could take, what, a 2 out of here and make that a 5. Take a 2 out of there and make it a 32. So what do you say, 45 over... Well, they're all powers of 2. That's how I did it. 2 to the 4th, 2 to the 5th, 2 to the 9th. So. Yeah. So 45 out of 512, does that come out to approximately 0.088? Wait a minute. So is this one more likely or less likely than the previous example? Why? Why?
Number of trials is higher. Failed.
Well, I could fail back here too. In fact, the probability of failure is bigger on this last one. It's like I chose those on purpose or something. Yeah, it's amazing how that stuff happens.
The number of trials increased.
Okay, trials increased. Does that make a difference?
Yeah.
Why?
More chances for
But the probability of failure here is lower. So I'm taking a smaller number to a higher exponent. I don't know. If you take a small number to a, if you take a number less than 1 to an exponent, it actually gets smaller. So does the number of trials affect it? Are your exponents going to be bigger? Yeah. And if you take a decimal to a bigger exponent, the number itself actually gets smaller. Okay. But then this front number gets bigger normally, depending on your x, right? See? Tough. How do you work that out? It really doesn't matter. It could go through. Now, if you want to do this one the other way, you would have to sit there and say, what do we want? 3 clubs? You say a quarter. This is the old way. A quarter, 3/4, 3/4. But these 3 could have happened anywhere. Those 2 could have happened. You'd have to go back through that combination. You'd have to go through that combination of basically, really 5 factorial over 3 factorial, 2 factorial because of the repeats. And oh, look at that. That's what we did. How about that? It's as if the formula just knows what we need, and we don't have to think about it. Interesting. Any questions? This is a big one, binomial. I told you I would talk about Bernoulli. What a Bernoulli distribution does is it still only has 2 outcomes, so that's the same. Okay, but it isn't a certain number of tries; it just does it once, and then you have to repeat that, simulation if you want to do it that way. So it only does it once, and then you'd have to add up how many successes you actually had. Yeah, it's very close. Bernoulli is very close, but a binomial is like they just added them up for you. Okay, is really the nice thing about that. So if I wanted to do something like example 4 with Bernoulli, I would have to sit there, do this 5 times, multiple times, and then try and add up how many times it actually worked versus how many times it didn't work, and then come up with the probability. That would take a while. So that's why binomial is nice. It just says, here you go, it's 0.088. That's so what, 8%? Well, we'll say 9 if we round. 9% of the time it'll work. In Bernoulli, you'd have to sit there and do it a ton of times, and then add them all up and find, about 9% of the time it works. So binomial is a lot nicer. But it's not bad for you to hear names and shortens. Maybe they'll come important later. Never know.